So what are we doing here, right? So we started with the last lecture. In the middle of last lecture, we did the Bernoulli process. Everybody can see, right? You can see it. Okay. So what is the idea? So you have a sequence of arrivals. So let's say you have n slots. And there is some underlying probability distribution P for success. Right? Success is 1, failure is 0. And I think if you take a small square inch of grass over there, whether a snowflake flew on the grass, snowflake hit that patch of grass, 1 if it did, 0 if it's not, and using a very simple averaging, you can figure out what the probability is, right? Given you can do some order of magnitude analysis. Okay. So this is probability of success. Right, and 1, 0, 0, 0, 1. Something like that, right? So in this particular example, you have had 1, 2, 3, 4 successes, right? The rate of success the number of successes is k, okay? So this is one realization. You run the experiment again, you might get the 4 successes, 2 successes. Very rarely you will have 0 or 10, whatever, right? You know that. And we saw that it's the probability distribution of Sn equal to k, which means probability that you have exactly k successes is given by the binomial distribution n k p to the power k 1 minus p to the power n minus k, right? And this is very easy to see. This is the probability of a particular sequence, and then this is in order doesn't matter. Only count the number, you get this binomial distribution. Okay. Any quick questions there? Okay. So now, especially in science, especially if you look at something like that, we like to take things in the infinite limit, right? We're still interested in counting, but in some kind of infinite limit. So what we do there is, we take a case where assume p is small, and n goes to infinity, right? So you're interested in a very large number of bins, so maybe it's a long process, or one other interesting way to think about it is I have some finite time interval. Okay, I have some finite time interval, and I want to divide that finite time interval into a large number of discrete units. Right? So that's the example that makes a lot of sense. Right? Because unless you're working in quantum mechanics, you never get time to be discrete. Right? Time is a continuous thing. So you want to divide time by a large number of intervals, and you want each interval to be very small so that you can track things at a high degree of with a high degree of accuracy. Right? That's the idea. So when p is small and n goes to infinity, and np is moderate, it's kind of a loose statement, but that loose statement is because if the probability of success is very high, then you don't really have, you just does not make sense, even randomness. I don't know what it means. And the same thing, if probability is very, very small, you can model rare events, but NP has to be moderate. Okay? And when you did the short derivation, the two-step derivation, and you also see for those limits to hold, you need NP to be reasonable. Right? So under these conditions, you get probability of Sn equal to k. I'm going to write it slightly differently, just so we can use it. I'm going to write it as e to the minus, lambda is NP, right? I'm going to write it as minus e by k factorial NP to the power k. So this is what you get in the limit of n going to infinity. You get the Poisson distribution. Last time I wrote NP as lambda, but there is benefit, and that's how everybody writes it. But there is benefit to keeping NP, and you'll see that in a couple of minutes. Okay. This is it's a very important distribution for many things, especially because a lot of what we do in complex physics is counting, right? Like energy levels. You take a very complex problem, split it into bins, and then you say how many categories can be fit into a bin, and then you get distributions of the bin, right? That's really how a lot of physics processes can be modeled, and many other processes. Anyway, any questions here? Yeah.
What if the data that we are studying is uncountable per se?
Sorry?
What if the data that we are studying is uncountable?
Is uncountable?
Yeah.
Well, then it's infinite.
Yeah, but it can be infinite, countable and uncountable, no?
Sorry?
That one can have infinity in both senses. Yeah.
True. So again, it has to be, first of all, this whole thing depends on some countability, right? Otherwise, this whole thing doesn't make sense. Yeah. Ultimately, you're saying, how many successes do I have? So that's a counting process. Yeah, so that's good. Keep bringing that type of baseline. All right, so now, let's now model the example that I showed in the last lecture, which is, I have it here. Okay, so yeah, let me show that video and then let's get back here. Are you sure people on Zoom are seeing the right thing?
They cannot see this.
They cannot see this. They can, right?
Good morning.
I'm typing in some terminal. Sorry?
It's slightly blurry. I think since you're not sharing the screen, we can see the window, but as of now, we are not able to make clear of the text. But that's all right.
Yeah, okay, give me 1 second. Really what I wanted to show is the following. Can you see this properly?
Yes, we can see the image. Yeah.
Sorry, what were you saying?
Not the legends here.
Not the what?
Not the legends.
Oh. Okay, so what do I have to do? Do I have to share or something else?
High level they can still see it. High level they can still see it.
Okay, anyway, I introduced this last time. This is in the notes, so just take a look. So anyway, here is a great application, which I didn't think it would work well, but it's a nice approximation here, right? So I have a sphere of diameter 2 sigma, then I have a whole bunch of particles that are distributed at random. And at any given time, I want to count how many times, or at what fraction of particles have collided once, twice, 3 times, etc. Right? So initially, and anyway, this orange line is the model, assuming Poisson of lambda t. I'll tell you how to get lambda. And then, so initial time, there is no collisions. And then after a while, you have a few fraction of particles that have collided. I have colored by number of collisions, so these particles have collided once. And then time moves on. It's a periodic boundary condition, right? So particles that left can come back in and collide again, right? So those green particles are particles that have collided twice. And I'm just showing a small fraction of particles, right? If I did, I ran those with maybe 100,000 particles or something. So that's, and I'm showing a subset of particles here. Okay, so that's the problem setup. Any questions on the problem setup? Because this is your, pretty much recreating this is your next homework. Yeah.
The homework problem mentions that we have to randomize the initial velocity, so it wouldn't look like this, right? We'll
Exactly. So it's an interesting problem setup. So in this case, the initial velocities were all, the initial positions are random, but the initial velocity is all pointing in the x direction. But there is some level of symmetry in this problem. So yes, in the problem, in the homework, I thought I asked you to also do the velocity problem, but there is also a setup that has random initial velocity. Interestingly enough, both can be modeled, and there is a level of circular symmetry here that makes both approximations work at the same level. But if you read the homework, I've asked you to do both. Okay, any other questions? Okay, so how do we model this using a Poisson process? We have all the elements already. But let's go through it explicitly because so how to model particle collision. Again, so these particles don't collide with each other. They are non-interacting particles. So assuming each is an equal member of ensembles is fine. So first, we want to derive what is called a collision rate. Okay. So I want to define collision rate as lambda. And basically, for a given, let's say for unit time, how many collisions do you expect? And for something like that, you can, if you're focused on a certain patch of grass, you can figure out, you can have some approximation of the velocity at which things are falling, some approximation of the density, and you can come with a collision rate, right? So this is what we will do exactly. Okay. So let's do that in our problem, right? It's going to be a crude approximation, but it's going to work. So what is the problem setup? You have, this is your domain, but it's a periodic domain. So this is 2 sigma This is L. And let's take the case where you have unit horizontal velocities. So you have a bunch of particles. There's a particle here, there's a particle here, particle here. So if you want to estimate collision rate, you want to say, okay, first of all, if you look at this from a physicist's perspective, and at least if you're only interested in the first collision, you would say, oh, only the particles that are here. Let me draw some kind of virtual domain. Only the particles that are here will actually collide with that circle, right? Otherwise, things will miss. Anyway, I'm only thinking about the first collision, not the second collision. But remember, this is a periodic problem. So all the particles in this, all the particles that are here also will collide with this, right? And if you're thinking, oh, this is outside the domain, just think of that being here, and we are still okay. Okay? So what is this area? Different color, but what is that area? No. Sorry, yeah, it's 2 sigma L, right? So that shaded area is 2 sigma L. And if you're looking at probability, then you want to divide by the total available area. And why is this reasonable? Remember, we are assuming particles are located at random in the square. So the fraction of particles that will collide will be just the area fraction. So 2 sigma L by L squared minus pi sigma squared. Right, shaded area divided by total area. But we want, yeah.
Do you not have to take into account the fact that you don't have particles starting within the sphere itself or the circle?
Oh, there are no, so this is a solid sphere, solid circle, so there are no particles inside.
So shouldn't it be 2 sigma L minus pi sigma squared over L squared minus pi sigma squared?
Sorry, what?
Shouldn't in your numerator, shouldn't you have 2 sigma L minus pi?
Oh, no, it is still 2 sigma L because remember, so whatever mass you lose here, you gain there.
I see, okay.
Yeah, and that's why I drew that part. Yeah, it's good. I mean, it's good to get into detailed understanding. But what we need is a rate. I want to call that rate a lambda, right? And that would be 2 sigma by L squared minus pi sigma squared, because that is unit velocity, right? So length is what? So length is velocity times time, and we have unit velocity. Right? Remember, even after collision, these are perfectly elastic collisions, only the direction vector, only the direction of the particle, the direction of the velocity of the particle changes, not the magnitude itself. Right, so this is the basically an expression for a collision rate. Okay. And it's, I mean, for this particular problem, we chose a particular L and a sigma, like in the homework, or like in the notes, so you're actually pretty good. So now we want to use that information. So anyway, so now what are we trying to model, right? Probability of collisions for a given time tau. Okay. So this is the time integral tau. And now I want to play the same game. I want to divide tau into n intervals. So 1, 2, and I want to call each interval as delta. So tau is n times delta. So this is where we are going from. So basically, this is where we're trying to go from binomial to Poisson. So we have that, and then remember, so NP is what, so remember the Poisson distribution here? In the Poisson distribution you have NP. So we have to somehow calculate NP. And how do you get NP? So what is NP? So before that, what is P? In this,
Probability of success.
yeah, it is the probability of success in that particular delta, right? That's how we defined it, right? What is the, when I drew this thing earlier, I said, what is the probability of success in that particular box? Right? So in our problem, what is P? Sorry?
Probability of a collision for some bin delta.
Yes. So that would be lambda times delta, right? So lambda is probability. Lambda is basically rate, right? So lambda times delta is going to give you P. So what is NP?
Now delta.
N delta lambda. So well, I'll just write it lambda tau. That's because that's how I've written. So again, we are still. I mean, this is still approximation, right? But this is approximation coming from physics, getting that into some kind of mathematical form. And like I say in the notes, this is your first predictive modeling challenge of the class, right? So you have some physics process. In fact, that particular setup that I showed is actually, in physics, it's called the Laurent's gas, and it has many, many applications, as we'll see. So even though it looks like a cooked up, weird problem, it's actually very relevant for a lot of physics. So anyway, so this is good. So we basically have NP equal to lambda tau. This was the key result. And if you go back here, that's why I wrote it as NP instead of, lambda. In fact, I would change it in the notes also when I introduce the, everywhere in the literature, it's written as lambda, but leaving it as NP is better because, let me write that. So probability that you have k collisions in our problem is e to the minus lambda tau by k factorial times n. Lambda tau to the power. Okay. And the reason why I wrote it as NP in the Poisson when we derived it, because this whole thing is written as lambda. I didn't want you to be confused. So in the notes I'll change that to NP. It's not the form, but it's much more intuitive. I think everyone should write it as NP. Not in any case. So this is a model. Any questions? Yeah.
When could this degenerate into a normal distribution?
So basically I said when when lambda is small, you basically get this. When lambda is large, you actually get to Gaussian. It's actually a really good question. I think I probably mentioned it in the last class. Remember, we start with a binomial distribution, right? No approximations there. Binomial is strong. You're not talking about low, high, or nothing. Binomial is binomial, okay? And then when we said we have small p, you're more or less modeling rare events. In the small p limit, you get the Poisson distribution. And in the larger p limit, you'd actually get the Gaussian distribution. But there are some technical facts there. But just like we had some technical facts here, right? We said moderate, this, that, and a few other assumptions. We got this. The other limit would be a Gaussian. Okay, any questions? Yeah.
So the lambda assumption that we make here in terms of the shaded area makes sense if it's uniform velocity in the x direction.
Yes.
But if it's randomized, maybe we look at a cone or...
Actually, symmetries in the problem make this work. I want you to explore it in your, So I think most homeworks don't take, there's obviously a minimum thing that I need, and then it's up to you. You figure it out, okay? And the grading will also be like that. Maybe the 0th homework we had, it was very prescriptive, but moving forward, I'll say explore it, right? So figure it out. We can discuss it. And trust me, I've not seen this example anywhere, and I came across this while I was deriving something for something else, and even I was surprised that it worked so well. So let's quickly go back to that video. Well, I've shown it a few times, and you're going to do it in the homework, so I'll spare you that. But this seems to work really well because of a few reasons. I have a few reasons in the notes. You can explore more reasons as you do your homework. But of course, it's not perfect. It cannot be perfect because remember, we said IID assumptions. We said no correlations. But obviously, once a particle has had a collision, it gathers some kind of correlation, right? So remember, for the Bernoulli process to work, we said memory doesn't matter, right? So if a whole bunch of things have happened, the next thing is completely independent of all of the things that have happened. Okay, so that's fundamentally what we use for the Bernoulli process. There is no memory. But once a particle has collided, it has some memory, right? It has built some amount of correlation, and that correlation is not modeled, but it still works. And in many derivations in physics, like the Boltzmann equation and the theory of gases and many other things, the number n is extremely large, and actually p is somewhat small. And I said last time, 6.023 into 10 to the power 23, right? So it's a large number. And many of these approximations we make actually are very good. And some of you, how many of you have taken a class, say, molecular gas dynamics? That's shocking. You've taken it, right? No?
Yeah.
Sorry. You're losing participation. Anyway, so a few more have taken it. To me, the better way to teach, so when you take kinetic theory of gases, you're asked to imagine a gas, right? It's a very complex thing. But at least my opinion is if you learn how, and then you're going to use some hand-wavy assumptions, but if you go through this route, you've not touched kinetic theory of gases yet. If you go through this route to do kinetic theory of gases, I feel you'll have a lot more understanding. That's all I want to say about this, and the rest you can explore in your homework. Okay, but I can take a question if you have one.
in the notes you talked